Welcome to the fourth lecture in our course on IoT. Today we're going to conclude the part on application areas, and we'll take a look at two of the remaining application areas. So this is our part one of that course, DVID 71, where we talk about different areas of applications and get an overview of this, and we'll continue in upcoming parts of that course with all the other topics on infrastructures, data management, privacy, security, and energy. So today we're going to talk about two topics which are still in this top 10. One of these topics is retail. So we are going to show some of the things you've probably seen before or you see in your everyday life when you go shopping. Some of the other things which are not that common here at the moment but might be common in the near future. And in agriculture, it's also very important to use IoT components in order to reduce the amount of manual labor that has to be done. So today, as I said, we're going to discuss retail and agriculture, and always we are going to show some examples and discuss some of the challenges and expectations results we can get out of the use of IoT in these areas. So there's a great review paper on a large number of IoT use cases in retail application. And there are quite a number of very different use cases. So some have to do with logistics, and some have to do with more automated handling of the whole shopping process. So one use case for IoT in retail applications is inventory accuracy. If you have worked in retail before, maybe as a high school student helping in a shop or something, you know that every store has to do an inventory for tax and financial purposes at least once a year. And this takes a couple of days in a large store because a large number of people, like students just hired for this job, have to go through the shop, find every article that's sold in the shop, make a count of this and enter it usually manually into a number of lists. These lists are then consolidated into complete lists of the numbers of each product, and then these are compared against what would be expected to be in the shop. So there can be differences, and there will be differences, sometimes just due to, incorrect inventory processes. So people just counted wrong or just assigned a count to a different article. Sometimes to other faults like things breaking and not being taken out of the inventory. And of course, there's one major reason for inventory differences, and this is simply theft. So people obviously taking things without paying for them, and in consequence, these are not registered in the cash desk, so you don't have this information in your online system. So inventory accuracy is very important to figure out your theft rate, to figure out how many things might break, and of course also how many of your things you're actually going to sell. So enabling inventory accuracy using IoT enables a retailer to know exactly what inventory is actually in store, not only once a year or whenever you count, but every minute, every second, because you know what's coming in, you know what's going out, and this is a near 100% accuracy. Obviously, if somebody steals an item, this can not be discovered by the electronics components in the IoT system, but in all other cases, you can find it. And even if customers walk around, take an item, and 5 minutes later they're in a completely different part of the store and figure out, oh, they don't want this item at all. Very many customers unfortunately don't bring the item back to where they took it, but they just put it in one of the shelves in a completely different part of your store. So this makes it more complicated to find stuff, especially if it's perishable stuff like frozen goods or fresh goods, whatever. So this is already very helpful. And of course, closely related to this is that you want to know when an article is close to being sold out. So you don't want to start replenishing your shelf when the first customer starts complaining, because then a lot of customers would have already left your shop without buying that article because it's not on the shelf, but maybe it's still in your storage room. So you want to have an alert for replenishments as soon as whatever the second to last or third to last item of a certain article is sold. Especially, you also want to do it at a subcategory level. Like, for example, you're selling clothes, so you have like trousers, but of course, these trousers might have different sizes, different colors. So you can figure out like if you're running out of trousers of a certain size and not of another size. I've already mentioned misplaced items, so it's important to maintain inventory in an appropriate location. So usually a store, no matter if it's a yeah, just grocery store or a store selling clothes or electronics or whatever, has well, certain parts of the store, and usually well, except for special offers and stuff like that, one component or one article is always stored in the same place. So you not only want to maintain inventory, you want to maintain it in the appropriate location according to your store layout, because your customers are used to finding an article in the same place. So when you move it around, and probably that happened to you already, it happened to me. So when an article is moved around in a store, your customers get confused and they really don't like the situation because they found this article in the same previous place for the last 10 years. So this will help. Then, of course, we are not only into tools that help a store owner or a store operator run the business, but we might also want to improve our business as a shop owner. So, in addition to all these logistical parts, we also want to, yeah, understand which articles the customer might be interested in. Maybe not right away, but maybe in the future. So, IoT can also help with what we call item consideration and the path to purchase. So, if you can find out what items are touched by a customer, because a touch customer looked at an article in a shelf and then maybe put it back, what articles have been tried on, like a piece of clothes or shoes or whatever, and what articles have eventually then been sold to a customer in the store, you get an idea, you get an insight into, yeah, how inventory moves as part of your customer's trip throughout your store. You get an idea of what might be interesting. So, like, is it just the customer coming in with a certain idea, I want to buy this pair of shoes and nothing else? Or is a customer just browsing and then maybe sometimes looking for high quality items, and some other customers might be looking for the cheapest option in the store. So if you have more information about this, this will help you optimizing your product, selling things. But of course, uh, it also means that the customer gives up more data about him or herself, which in the end is an interesting consideration regarding data protection. You also want to map the path of customers through your store. So you want to figure out not only if the ways through your store is large enough for like the customer passes that are commonly taken, but you also want to figure out what's the most common path through your shop. And then, of course, you want to incentivize customers to buy stuff. So you put all the great offers are not the offers which are cheapest for the customer, but of course, those are the offers which make you the most money, obviously. So you want to place them directly into the path of the customer. So you want to place them where most customers actually walk through your store. And this is, of course, also related to layout optimization. So, in general, you want to optimize store layout, product placement. Uh, Optimizing not always means that you want to enable your customer to take the fastest way out. That might be useful in whatever, a small supermarket. Optimizing sometimes means that you want the customer to take the longest way through your whole store, just because the customer might want to buy something else that the customer hadn't thought about when entering your store. And of course, you can see great examples for this in the local stores of a large Swedish furniture chain. And of course, in the middle, you also have a restaurant. So if the customer gets tired while walking through your shop, the customer can get some refreshments at cheap prices and then have more power and more energy to buy more stuff. Right. So these things can get pretty advanced. So one thing that's was common in retail is that it's relatively intensive in terms of person power that's required. So you need quite a number of people Not only the cashiers, but people replenishing shelves, people taking care of deliveries, people taking care of security, people taking care of your storage, and maybe in larger stores, separate people selling like meat or bread, or of course in yeah, whatever non-food stores, people walking around helping the customers to find things and so on. This is, of course, very expensive because you have to pay all these people, even though people in retail stores are unfortunately not paid very well. So this picture here is an example from an application note, or in this case, a use case study by Intel. So Intel has invented a RFID, so radio frequency identification based sensor platform, and appropriate management software to more or less automatically run stores while requiring as little personnel as possible. So here we have a number of sensors. So on the left hand and on the right hand side, you have these points identified with a number one. So these are sensors which enable the store to run an automatic inventory management, and then, of course, you also have edge computing. So you have a server standing there. So all these sensors communicate with this central machine, but it's still in your store. So we call it an edge computing device, and not somewhere in whatever the headquarters of your company. So you get a local overview of your store. And you not only get an overview of the wares that go out of the store, but you can see the truck in the back of the picture. So whenever a new delivery comes in, you can automatically figure out which wares have come in with the current delivery, and so you know that you can update your inventory lists immediately to, yeah, figure out if there's something missing, if you have to order something more from your headquarters or from your suppliers in order to keep all your products active. And very many stores have problems that it's difficult when you have a large number of articles in your store to keep everything up to date. And one thing that has to be kept up to date nowadays very often is prices. So back in the old days, usually you had a price tag on each of your articles. So there was a person going around with an automatic machine that dispensed price tags. So in that machine, you could just configure the price like whatever, um, 9 kroners for something, and then this machine printed the price on a small price label, which was adhesive, and that was then attached to this article, like whatever, a can of beans, for example, right? And now, whenever you had to change these prices, then this person had to go around and attach new pricing labels to all of these products. And this also incentivized customers to maybe switch labels because, well, do you have expensive cans of beans and less expensive cans of beans? And of course, if you can switch the label from a less expensive can of bean to the more expensive, well, you can get that one cheaper as long as the cashier doesn't notice. So these prices were then really typed in by hand into the cash register, and then you had to pay the price. So, of course, whenever you wanted to update the price because, well, of price changes, inflation, whatever, or because you had a special offer that week where you reduced the prices, but only temporarily, yeah, a number of persons had to go around your store and update all these price tags. Now, that's a lot of work. So, an optimization, especially in these large chains of convenience stores we have, was, yeah, no longer attaching the price labels to the product, but uh, yeah, the price labels were then attached just to the shelf. So every region of a shelf where an article was located had its price label, so the customer could look at the price label and could see, like, if you had your store in order, so if you had the articles next to your price label, what does it cost? Now, this had a problem, so the customer put the article on the whatever conveyor belt at your cash register, and so, yeah, you had to know the prices of the article as a cashier. And of course, this is impossible when you have several thousand articles. I know a large German supermarket chain, Aldi, actually tried this. So Until a couple of years ago, the cashiers at this supermarket chain had to learn the prices of all articles by heart and had to have them in their head and enter a four-digit code for each of the articles when instead of having a more modern method. Of course, you all know this more modern method. This method just means that every article has a unique bytecode, so you have seen this EAN, European Article Number, bytecodes here, bytecodes, excuse me, barcodes, of course. So these can be scanned using a relatively primitive device. So instead of a price label on each article, now you have a piece of the paper, plastic, whatever packaging of your product that contained this barcode. And this barcode then in turn can be scanned at the cash register. And then there's a lookup of the price, so there's a database attached to that cash register. So you have a price for every article with a barcode, at least optimally. Of course, here's also a number of problems. So one thing that can happen is that there is an article that is not registered in your cash register, but the customer found it on a shelf, so somebody forgot to put it in a database. And it could also be that the price on the shelf was a different price than the one in the cash register, because, for example, the price had to be increased in the cash register's database, but you still had the old, cheaper label on the shelf, and that makes your customers angry, obviously. So, what would be great here is to have a system that enabled a shop operator to keep the price labels of the shelves updated, so synchronized to what is in your cash register. And this also enables you to adapt prices quickly. So if you know that there's an article that is in high demand because whatever, it was just featured on TV or on TikTok or wherever, and people are buying it like crazy, you can increase the price a bit because customers will buy it anyways. And so you can do it right away. You can do it from your office as a shop owner. You don't have to walk around your store changing labels. And of course, you no longer have to print price labels. This is costly, this is error prone, this is labor intensive. So now what you want is actually something that automatically updates the price that's shown on your shelf and keeps it in sync with the price that's in the database of your cash register. And in theory, we could have built devices like this for many years because LC displays exist for like 20 something years. The problem is LC displays, the early ones were hard to read because, if you remember old calculators or something, there is something like gray on green. That's not really nice. And the other thing is they use quite a lot of power. And usually you don't have a power line running through your shelves, except if it's a cooling shelf, obviously, or something. So essentially, it's very problematic to build this with traditional technology, and you would have had, relatively expensive hardware components like 20 years ago to realize this because you maybe needed to install cables to keep the labels updated. Now, with IoT technologies, we have an advantage. Of course, we have cheap, wide range wireless technology, so you will be able to reach all parts of your store. For example, with Zigbee, IEEE 802.15 wireless, or maybe also Bluetooth solutions for smaller stores. So this would enable you to have autonomous tags that can be updated over radio. The other problem now here is energy. So how do you supply such a tag with energy? The problem is, well, you don't want to run a cable and you don't want to recharge batteries every day in all of your 1000 something price labels in your store. So you need a device that's relatively low on energy consumption here. And the biggest part of a traditional label would have been the display itself. So the LC display, for example. And here, another electronic component that has come up in recent years is really important to get this to work. And this is e-paper. So e-paper, electronic paper, is a technology which, essentially enables a display like shown on the lower right-hand page. So this consists of just black and white pixels. Some e-paper displays also have a third color, a highlight color, in this case the red color. There's also some with yellow color. Maybe you've seen some of them. And of course, if you have one of these ebook readers, you already know e-paper. So e-paper is a technology that's relatively easy to build because it's just like little balls of plastic, and they're white on on the one half and black on the other half, and you apply an electric field beneath these little balls that are sitting between two sheets of transparent plastic. And depending on if you have a positive or a negative charge, then either the white part of that ball is moving upwards or the black part. So essentially, you show white or black pixel, and with a bit more control, you can have three colors, like this additional red color we show here. Now, the good thing about this is a physical display component. So essentially, you're just moving these little balls in one or the other direction. So you're just rotating them by 180 degrees. And if you switch the power off, they just keep their location. So that means that you only need energy to receive new pricing information. And then when you receive this new pricing information, you have to update your display once. But after your update is done for the next days, weeks, maybe months, depends on how long your price stays stable, you don't have to spend energy because all this information continues to be displayed thanks to the e-paper display here. So that's pretty important. And e-paper technology has become cheap enough that you can actually afford to equip your store with several hundreds of thousands of these labels. And the good thing is that there's integrated radio solutions, so you can buy a very relatively inexpensive chip to drive all these things. For example, there's a Texas Instruments controller called CC2530. This contains one of the oldest microcontrollers that ever existed. So that's based on Intel 8051, which has been introduced around 1980 already. The good thing about an Intel 8051 is that all the patents for this thing have run out. So in turn, you don't need to pay any licensing fees if you want to build a system based on such a microcontroller core. And that's what Texas Instruments did. You don't need much computing power, but still this 8051 has radio built in, like a Zigbee radio, and a bit of flash, so 256 kilobytes, and a little bit of RAM, so only 8 kilobytes. But that's more than enough to run such a simple application like an electronic price tag. And here on the lower left-hand side, you see a proposed tag of the price of such a price tag with the previous version of that Texas Instruments chip, the 2430, which is pretty identical. So you can see that in essence, the most of the components are integrated on that chip. So not only the microcontroller, but also display drivers, wireless components, and so on. So essentially, this is a one-chip solution with a very simple antenna and an attached display, which can be controlled over a very simple interface, like for example SPI, because you don't have to update that label quickly. It can take a second or two to just update that information. Nobody cares. You're not going to play videos on these. Though there are relatively fast e-paper displays nowadays available, of course. And if you buy these e-paper displays in bulk, they can cost in the region of single-digit dollars. So that's relatively affordable, and these things are uninteresting for customers. So usually customers don't try to steal them. So that's a nice thing. Of course, you still need to have some yeah, pruning, like automatic configuration of these things. So when you send a price update around, the price label doesn't accidentally update with a price for another product. Of course, you can show more information, so you can show whatever this required information of not only the price of an article, but the price per 100 gram or per kilo as required by the EU. And of course, you can have these red labels like yeah, informing the customer, oh, this is a special sale price or whatever, or this is just available for a short time and might run out soon, and so on. So that's a very nice solution, and I think that's a very typical IoT solution because it includes very many components, like yeah, relatively innovative technology like e-paper displays, traditional embedded systems technology like microcontrollers. It includes central data management in the store because you have a central database that's also connected to cache registers, and these have to be kept in sync. You have a large number of distributed devices here in your store, so one for every article in your store, for example. And of course, you have a wireless network connection connecting all of these together in a larger network. And a combination of a number of these technologies, so smart price tags, RFID technologies, and quite a lot of more technology, was employed by Amazon to implement real staffless stores. So these are called Amazon Go. They don't exist here at the moment, but they have been started in the US and in the UK. And the idea is that a customer can walk in. The customer can then identify him or herself, either using a smartphone app, or you can even have something like a fingerprint reader as identification. And then you have to have this Amazon app, you have to have an Amazon account on your smartphone. And then when you walk through the store, you have large numbers of cameras and additional sensors, which means that the system in itself, so the electronics system in the store, can figure out which articles you took from a shelf. So when you leave the store with these articles, so it also needs to figure out, of course, which articles have to be put back by the customer on the shelf. And when you leave the store, well, the amount you have to pay for the articles you actually took out of the store is automatically deduced without a cashier and also without a self-checkout station. That's the interesting thing here. And as you can imagine, you need quite a lot of technology to get this to work. So in these Amazon Go stores, there's like lots of cameras, up to hundreds of cameras mounted in the ceiling. And these cameras use computer vision and deep learning algorithms, and they fuse with additional sensor information, like, for example, RFID sensors, ultrasonic sensors, and so on, to really figure out what the customer is doing. And this is done for purchase, for checkout, and for the ultimate payment then. Of course, this is integrated with your Amazon Go app, with your account, so the money is automatically deduced from your Amazon account. Now, the problem is like, first, there can be quite a large number of customers in your store, and these customers each buy more than one product, maybe. So the system initially had lots of problems really differentiating between multiple users, tracking these users throughout the store, and also tracking which user actually took which object. Just imagine there's some offer on the shelf, and 10 people stand around it, and each of these grab one item, but one of them might not. So who is the one who did grab that item? Because that person doesn't want to be billed for that item, obviously. The system also had problems with items moved to other shelves, like imagine kids running around your store and moving items just for fun to another shelf. Then the system had a hard time really identifying which item it was that was taken out, because initially that system identified articles with the shelf location they were assigned to. So if you took an article from a piece of the shelf it originally not belonged to, then you might have gotten a wrong article or the system was unable to identify it. And one thing I see a bit critical is like, how does the system actually differentiate between different customers? Now, of course, you can't implant, or at least I hope they are not trying to implant customers with their own RFID chips to identify them. So there need to be other methods. And what this computer vision system was implementing in the Amazon Go store is body habitus, so analysis. So each person is different in the way you move parts of your body, so different in the way you walk, different in the way you move your fingers, your arms, your hands, your head, and so on. And the system really tried to identify the customer. And of course, to do this, you also have to assign all this information to that customer in order to charge the customer for the wares the customer bought. This is, of course, very critical just because, yeah, this information, if it leaks somewhere, and imagine you have a public surveillance systems like in other countries with many hundred cameras put in public places. You could be followed around public places or the subway station and so on. And this is not science fiction, unfortunately. Systems like these exist already and are used. So people in densely populated areas can be followed around and there can be a trace of, yeah, the locations you walked to or the trips you took on the subway or on the bus. And this is a very shocking situation. So the question is, do you want to trust Amazon or whoever is going to implement such a store with data like this? And technologies like these are not just like, oh yeah, high-tech demonstration for what Amazon can do. They're spreading. So I came back from a trip to Trondheim in Norway yesterday, and there's a store selling regional products from Trøndelag, so the Trondheim region in Norway, and the central station in Trondheim. And this was also a staffless store, and there was a little warning sign at the door. Caution, here's camera surveillance for everything, so to help you behave. I didn't enter that store. I don't want my data. I don't want this information to be, yeah, just stored by whoever. You don't know who it is, right? You don't know who operates that store. And having a store owner telling me that it needs technology to control how I behave and that I behave. I don't think that's the right way to go. On the other hand, of course, there are regions, for example, I've seen reports about small Swedish villages in the middle of nowhere, where the problem is that it just doesn't make sense to have a manually staffed store because there's not many people living there. But of course, these people need to buy things. So there is a trend towards automated little stores, which might be helpful. So it's an interesting trade-off to see. It's a matter of question, like whom do you trust with your data? But as you can see with the example of the staffless Amazon Go stores here, you need a large amount of investments. You need all this technology in order to get this to work. And I'm not quite sure if it's worth it because a lot of people will also be put out of work by this technology. And not only students are relying on like holiday jobs as a cashier or refilling shelves, but there's of course a large number of people doing jobs like these. And yeah, these people will be out of work then for, yeah, I don't know, just improving the profits of the store owner. I'm not sure this is the right way to go. So it's really interesting and important to keep an eye on this, I guess. So if you want a bit more of an insight into how this Amazon technology works, uh, Amazon has tried to patent a lot of this technology. So here are some excerpts from the Amazon Go patent here. Uh, Patents, so this is, I think, not yet granted, this is applied for. Patents do not necessarily describe the way something's implemented, but a vision for something that maybe doesn't have to be implemented. But it seems that some of the stuff that's in this patent, which is linked on the references side, is actually implemented in the Amazon Go stores, like the hand recognition we are showing here on the left-hand side. And on the right-hand side, you see an overall structure of the system. So you have shelves which are filmed by cameras. So whenever a customer approaches a shelf, you have a picture of yeah, the shelf before the customer was there and after the customer was there. So you can check out the difference. And of course, you can imply that the customer took it. You can identify the customer using the specifics of, for example, walking gestures and so on. And then you all have all this connected, of course, to your central inventory and caching system, and in turn to the Amazon cloud in order to connect this to your Amazon app, to your account on your smartphone. So this is a very complex thing. And as you see on the right-hand side, Amazon imagined implementing more sensors. So there's something like smart floors that can identify where someone is walking. You have depth sensors, so you can maybe figure out how many of an article are sitting behind each other in the shelf. You can have buttons for like dispensing something like whatever, a piece of bread or something, touch sensors, microphones, instrumented uh, auto-facing units. So that might be face recognition, weight sensors, proximity sensors, optical sensor arrays, magnetometers, gyroscopes, accelerometers, an RFID reader, and optical sensors. So essentially, these stores, if they implement all of these, are a complete surveillance for the time you're in there. This is obviously required in order to avoid theft. So I'm not sure how effective it is or efficient this is. But nevertheless, you'd have to put a lot of trust into the store operator in order, yeah, to really be comfortable using such a store because you have no idea how long this data is stored, where this data is going to end up, or if some hackers are going to break into the systems in order to gain access to that data, or maybe even a hostile operator from the state side who would be very interested in implementing video surveillance or person surveillance. So As I said already before, IoT is a technology that can be used for good and bad. And it's always good to keep a critical eye on this IoT technology. So that's why I'm telling you both sides of the story. Of course, it's very convenient. You don't have to take any cash. You only have to remember your smartphone. You can just walk out the store with all the stuff you have. But there's a price to pay for it. And that's not only the articles you buy, obviously. Now, this other area of application I want to talk about today is agriculture. So, as you can imagine, agriculture traditionally also has been very labor intensive. This has been reduced significantly by the introduction of automatic devices like tractors and all this farm equipment, but still uh, in agriculture, you usually have large amounts, so large amounts of area, like fields where your crop grows. So what you want here is you want to do some precision farming. So you don't want to provide water on the same level for your whole acres of field, but maybe you want to apply water or nutritions or pesticides selectively. So this is an application area for IoT in agriculture. We call precision farming. So this not only has to do with farm management, so buying required like feeds for livestock, required grains for planting whatever wheat and so on. This also includes being able to monitor the soil of your fields, to monitor disease in your crop and in your animals, and also trying to control it, to control and monitor irrigation. So this should happen outside, but you can also have, of course, inside management of greenhouses where you grow plants and you want to monitor the plants. You want to enable a climate mapping, maybe have sections of your greenhouse with different climates for growing different sorts of plants. And of course, you want water management. If you grow animals, then you want to have animal control on the one hand for your livestock. So if you have livestock that's running around freely, like maybe sheep or cows, you want to figure out where they are, but you also want to check their health. So you want to check out, is there a sick animal? So you want to check out the heart rate, maybe the body temperature. And there's also, as we see in a bit, methods for gesture recognition, but you can also try to control animals that you don't want to have, like pests trying to eat your crops. So you could also try to figure out if these are approaching, like maybe birds trying to eat your fruit and whatever. And you could try to repel them, maybe using ultrasonic sensors. We'll see an application in a bit. And there's a number of challenges. Of course, security is always a challenge, but a more important challenge is that the people applying this technology, they usually farmers are very technically knowledgeable because they have to keep all their equipment running, but nevertheless, they lack specific knowledge of IoT technology so far. Maybe we can shape this with courses like this, but nevertheless, we have to find methods to enable a farmer to set up such a thing because you don't want to replace your farm workers by an expensive maintenance engineer coming in every week and fixing your IoT systems. Then you just probably spend more money on that. One important thing, especially if you run your whole system outside, is reliability. For example, you have to be able to adapt to rapidly changing environmental conditions like sun or rain, low or hot temperatures, freezing, and so on. These systems have to be scaled over large areas or large numbers of animals, for example. And of course, systems like these have to be interoperable. You cannot probably expect to buy all the components for your farm from one vendor, but you might need to buy them from different vendors, and then you need to mix and match them. And of course, you want the interoperability and able to get the complete overview of what's happening on your farm. So, one example here for precision farming has the objective of cultivating the soil for a specific crop, and this crop is cultivation of turmerics. So the quality of normally grown turmerics is not that great, and yeah, people found out it can be significantly enhanced, so you use them to produce curcumin. And in these enhanced plants, which can be enhanced just by cultivating the soil better with better nutritions and the right amount of moisture, then you can have the concentration of curcumin up to 5 times higher than in regular existing products. And the paper number 8, which is referenced here, describes a very complex system setup here. So this uses quite a number of IoT components. Obviously, you want something like a weather station to figure out not only the sun intensity, the rainfall, but maybe also things like air pressure and something like this. And you also want to predict, of course, future weather for the next hours in order to prepare your plants. You want to have soil sensors. For example, you want to measure how much water is contained in your soil, maybe conductivity, whatever is important for soil. On the other hand, you also want to control pests. So you will need to figure out, are there insects? How many insects are there? Do you have to do something against these? If you want to cultivate your soil, you need actuators for soil cultivating. And in the end, you also want to just control your whole system. So the system proposed here uses a smartphone dashboard application to actually monitor and also to control your whole system. And this uses a number of sensor platforms, which are very simple in this example here. So they are based on AVR-based Arduinos, and the connection over the field runs both with wired and also with 4G links here. So for details, as always, please refer to the paper here, where this system is described in much more detail than I can explain it here. Right. Uh, Another interesting application I found is this one here, animal monitoring. So animals are uh, not only useful for whatever, and like in the example of sheep here, for getting wool and milk and maybe meat from the animals, but animals are also very helpful to control, especially plants you don't want to have. So weeds. And what you want is, as a very eco-friendly solution, not to put out pesticides to get rid of your weeds. If you do a bioproduction, you're not allowed to do this, obviously, but you want to use animals that feed on the weeds, and so just remove them. So the problem is that you usually have useful crops in between the weeds, and of course you don't want your animals to eat the crops you're going to sell later on. So one example here is having animals like sheep or goats grazing in vineyards, and they're obviously only want them to eat the weeds and not your grapes. So this obviously requires additional support to what's called the animal husbandry activities. So you want to monitor and condition the behavior of the sheep. And you can do this, for example, by figuring out the posture of that animal. So it's a bit similar to what Amazon does in the Go stores to control the behaviors of the customers. Here we're trying to control the behavior of sheep. Well, the sheep are not going to complain, I'm afraid. And this is a method to actually enable sheep to graze in a cultivated area, like a vineyard or an orchard, without really eating the crops or eating the bark from the trees or whatever. And in order to do this, you actually have to figure out what the sheep is doing. And here, this posture recognition actually figures out the location of the sheep's head while the sheep is grazing. So if this location, if the neck pitch of the sheep, like shown in the middle picture here, is facing downwards, the sheep is eating something from the ground, so which is grass or wheat. So this is perfectly fine, and you should allow the sheep to do it. Whereas when the sheep's head is up and it's eating something, well, then obviously you want to avoid this. And here you have quite a number of sensors again, and applied machine learning to actually classify the use cases. And whenever there's a use case, that indicates the animal is standing up and reaching for food instead of having its head down, then there is at least an alarm. I have not found out what's actually happening. So if there's like conditioning methods like slight electric shocks or something, I wouldn't like this. But I can imagine people thinking about solutions like this. Similar to electric fences, so it's not really hurting the animal, but still it can be, yeah, a bit intrusive. Well, to condition the animal not to eat the crops. And then we can also have pest control. So you want to prevent the intrusion of animals, no matter if it's insects or maybe birds or whatever, in a field of crops. So usually you have like these traditional scarecrows scattered around your wheat fields and so on. They're not really helpful. I mean, especially, yeah, there are so many intelligent birds out, like ravens and crows. Just ignore these. One thing you can do to repel animals is to use some sort of, yeah, signal or method that really annoys them. And one approach is to create ultrasonic noise, which we can't hear. So our human hearing range is usually constrained to a top frequency of below 20 kilohertz, but very many animals are actually able to hear higher frequencies. So, for example, if you have a dog, dogs react to dog whistles, which have a frequency somewhere between 20 and 40 kilohertz. We can't hear them. So, if you blow a dog whistle, you can't hear it, but the dog will hear it. And if you're lucky and the dog is trained, the dog will come to you. And you can actually use something to also drive animals away. So here we have a system that is a repelling and monitoring system to prevent losses and damages in agriculture. It should especially monitor and prevent the attacks of wild animals and also monitor weather conditions. And this is not using chemistry because, yeah, of course, chemistry is expensive and not good for the crops and the customer. But this audible repeller, which just consists of an ultrasound generator, which runs between these 20 and 40 kilohertz frequencies I mentioned, and it's relatively loud. So 120 decibels is quite loud. So don't let your dog run there, I guess. These things are extremely cheap because they've been produced in millions and millions of pieces, because they're also contained in other devices. Like, for example, your vacuum cleaning robot will have an ultrasonic generator in it in order to detect walls. So it just sends out ultrasonic signals and receives the reflection from walls or from pieces of furniture standing around. So these things can be had for like $1 each, which is relatively cheap, obviously. The systems also have some sort of intelligence inside. So in this case, a Cortex ARM M0 plus microprocessor. So you can also get them for $1 about. And this is, yeah, capable of generating the frequencies for the ultrasonic generator. And this is also responsible for doing the networking with the central part of the farm, with other devices distributed around your field, and so on. For this example here, the transmission of signal is using IEEE 802.15.4. We'll go into details of all these protocols in the next part of the course. The transmission frames are very short, like 11 bytes long. They can be transmitted over like 50 meters, which seems to be a range that's wide enough to communicate at least to the next station, and to detect animals, and also to save energy. It uses a passive infrared sensor. So larger animals, for example, of course, give out heat. So using an infrared sensor, you can actually detect the heat source coming. Of course, this sensor can't differentiate between whatever a cow and a human. So essentially, it would maybe also activate when a human comes there. But this is a very good method to actually save energy, because the device does not need to be activated when there is no animal to be repelled, or human, who knows. And some of these devices can run on batteries, but these batteries do not have to be charged manually. But as you can see in the picture on the top right-hand side here, they use medium-sized solar panels in order to recharge the system here. So on the right-hand side, you see a bit of a network infrastructure that is used here. So you have a weather station monitoring the conditions. Then you have a number of these sensors and repeller devices distributed, which all connect to a central station, and then to a backend device that also can allows you to monitor your fields without being physically close. So These were two more application areas we've seen, I think two interesting ones. The retail applications are really, really high tech. So they use a lot of cameras and a large number of other sensors in high-end configurations to enable sensor fusion. So to use the data of multiple sensors simultaneously, bringing them into agreement. So figuring out, adding information to the output of one sensor with the output of another sensor to get more complete view of what's going on in your surroundings. They use methods from image and video, person recognition, machine learning, artificial intelligence methods in order, for example, to identify customers, to identify a change to a configuration of a shelf. They have to be very secure. So, of course, retail applications don't want to be hacked because that can get expensive. And nevertheless, because you have to put them in every store and maybe a large number of them, these still need to be somehow low cost, wireless, and some of these, like the electronic price labels, also have to be low power because putting the infrastructure in place for powered and maybe cable network devices would be far too expensive. IoT in agriculture is a problem that's more distributed. So you have maybe large scale distributed sensor networks. You might have moving targets like animals that still need to be able to communicate, maybe even without a central infrastructure. Some of these devices use energy harvesting because you're out in the field and you don't want to really charge your batteries there. And of course, these solutions have to be dependable. They have to work with hard conditions in harsh conditions because they're outside in the rain and the frost and the hot sunshine. So essentially, uh, these challenges here are a bit different from retail, but nevertheless, I guess they fit in with the whole IoT problem area we've discussed so far. So IoT still provides benefits for both of these areas too. So you have connectivity, you can have real-time online monitoring, you know what's going on either in your shop or in your fields or in your stables, and you need uh, low cost, low energy wireless solutions. And these are proliferating thanks to the introduction of IoT technology because so many things like these ultrasonic sensors or microcontrollers that you can buy for less than $1, or the e-paper displays. So this proliferation of billions and billions of IoT devices enables us to build low cost devices, and then we have optimizations for low energy and also the inclusion of wireless technologies that would have cost a large amount of money just 20 years back. So these were a number of examples of application areas with specific examples discussing certain challenges and also critically looking at some things like the amount of data that's collected about you by these IoT solutions. And of course, what's interesting to you is probably what's the technology behind it. And this is what we're going to dig into. So, in the upcoming lectures, part of that course here, we will discuss, these four remaining topic areas. And of course, we will refer back to some of these example use cases here and some others in order to give you details and show you how things are implemented in the real world. So the next part will be about the networking and infrastructure. So we'll talk about everything networks, so hardware, software, especially also network protocols, how to interconnect them using gateways, or how to use them without a central infrastructure, so-called mesh networks. And part of this is also the remaining hardware, so the sensor technology, the hardware platforms like microcontrollers, DA/AD converters, and also the software driving this also, especially system software for IoT devices. So which operating systems, for example, would you run for a small IoT device? The part after this is concerned with all the data that's gathered, produced, and consumed somewhere, so data management in IoT. So this is concerned with the collection of data, with its storage, how this is processed, analyzed, automated, and also presented. And then we talk about two areas which are so-called non-functional properties of systems. So one is privacy and security. I have mentioned privacy problems before today. So surveillance of persons or of animals, behavioral pattern analysis, but then also how to keep your IoT system secure. So by providing encryption, how do you provide firmware updates for devices that have security problems? And of course, which are actually the attack vectors that an intruder might want to use to attack your system. And the other non-functional property is energy. So we are taking a closer look at where energy is consumed in such an IoT system, how we can monitor this, how we can actually harvest energy from the environment so we don't need batteries or a cable to power connection. And then if we run mobile devices, so devices operating on battery or energy harvesting, we want to find methods for energy optimization. So essentially to increase the lifetime on battery of your device. And there's a special technology called intermittent computing, which is an interesting one we are also going to discuss in the run of this course. So that's all for today. Here are a number of literature references, and as always, I recommend you, if you have an interest in one of these specific topics. So these are sometimes papers, some of these are newspaper articles, and the Amazon patent is mixed in here because it's an application area. In upcoming sections of this course, we'll dig more into scientific literature because there we get closer to the technology and further away from the application areas. If you have trouble finding one of these papers on the internet or accessing one of these papers, let me know and I can try to send you a copy. But usually these papers, if they're not available directly on the internet, should be available if you connect using the VPN to the Karlstads Universitäts network. And then usually we have licenses, for example, to access papers at IEEE ACM, which is where most of the references in this intersection area between computer science, networking, electronics, and electrical engineering actually is published. So take a closer look if you're interested. Maybe it's an inspiration for you if you have worked in one of these areas before. Yeah, that's all for today's lecture. Thanks for listening. And we will continue with the next part with the infrastructures in our next lecture and video. Thank you. Bye.